Okay, this is a bonus lecture, you might say, in response to a question on Piazza about the homework solution for plotting the unit ball of a weighted inner product. So I appreciate the question because it turns out the solution in the homework was wrong. And so I will kind of walk through how one would do this correctly. So the situation is, and I'm just going to deal with two-dimensional vectors right now. So we have x is in R2, and we define the inner product as y transpose AX, where A is some. It turns out we need to have a symmetric positive definite matrix. So A, B, B, C. So that's the symmetric. We haven't proven the positive definiteness of it yet, though. So the question is, if we have the norm of x being the square root, I'm going to indicate that this is the weighted inner product by putting a subscript A on all of these. If we define our norm as the induced norm from this inner product, how do we plot the unit ball? Well, this seems like it should be pretty straightforward, and in a sense it turns out that there is a fairly easy answer to understand, but getting there might take a little bit of work. So the first thing you might be tempted to do is to just write this out. So we could say norm of x is equal to x1, x2 times a, b, b, c, x1, x2, and we're going to get a nice quadratic form that essentially looks like ax1 squared plus 2b x1 x2 plus c x2 squared, and we want that to be equal to 1. And so we pull up our handy plotting program and we just plot it for all x1 and x2 is equal to 1. So you've probably seen things like this before in your geometry class way back in kindergarten, and remembered that this was one of the harder parts of analytic geometry to understand, how to actually plot these types of things. So this is either going to be an ellipse or it's going to be a hyperbola. So if it's hyperbola, it's not going to be defining a valid norm, and also nor would it work with it as a valid inner product. And you can push that through, and actually the analysis shows you that that's why we have to have A being positive definite. If A is positive definite, then we get the ellipse. But regardless, we're going to have to figure out how to do that. So we know it's an ellipse. It's going to have some major axis and some minor axis. And we just have to figure out what that is. And we would pull out our geometry textbook and we would figure out the way to proceed. There's another way that's a little bit easier, and it kind of jumps a bit ahead of where we are in class right now. But if A is symmetric, positive, definite, then A will have unique orthogonal eigenvectors. So for A greater than 0, A has unique orthogonal eigenvectors. And if A has orthogonal eigenvectors, we can also make them orthonormal. In other words, make them have unit norm. How? Well, if A is an eigenvector, or X is an eigenvector, so let me choose something different. If V is an eigenvector, then A times V also is an eigenvector. So let's take, if we have two unique orthogonal eigenvectors, we can express A or X in terms of those vectors. So let's do that. We'll say let X equal A times the first eigenvector plus B times the second eigenvector. So now let's go back to our norm. We're not going to work with the square root of the inner product, because we just want to define where it's equal to 1, and the square root of 1 is 1. So let's just go with solving the equation. Solve X transpose AX is equal to 1. All right, so this gives us A V1 plus B V2 times A, that's transpose, A V1 plus B V2. That would be A V1 plus B V2 transpose A times capital A times little a V1 would be lambda A lambda 1 A V1, and likewise here we would have was B lambda 2 V2, where lambdas are the associated eigenvalues of V1 and V2. Okay, moving forward. Now we have A squared lambda 1 V1 transpose V1 plus AB lambda 2 V2 plus BA lambda 1, oops, I left out something here. That's V1 transpose V2 plus BA lambda 1 V2 transpose V1 plus B squared lambda 2 V2 transpose V2. Now we defined, we have orthogonal, actually orthonormal, eigenvectors. So V1 with V2 is going to be 0, and V2 with V1 will be 0. And V1 times V2 is going to be 1, V2 times V2, and V1 with V1 will be 1. And so this simplifies down tremendously to A squared lambda 1 plus B squared lambda 2, and we want this to be equal to 1. So now we have a much simpler equation to follow. So what does this tell us? Well, this can also be written in the form let's see. Basically, we know what we have here is once again the equation for an ellipse. It's parameterized by with independent variables a and b, and parameterized by lambda 1, lambda 2. Okay, so a solution to this is we can let A equal cosine theta over the square root of lambda 1 and B equal sine theta over the square root of lambda 2. Now we can just double check. So a squared lambda 1 is going to equal cosine squared theta, and b squared lambda 2 will now be sine squared theta, and when we sum both of those up, that's equal to 1. Okay, so we have now a parameterized expression for all values of x that give us a norm of 1. And remember, we had essentially the x is equal to AV1 plus BV2, which is now equal to cosine theta over the square root of lambda 1 times V1 plus sine theta over the square root of lambda 2 V2. And we just need to choose the theta, and if we it'll repeat after we go from 0 to 2 pi, so we just let 0 or theta range from 0 to 2 pi. Let theta be in 0 to 2 pi. So I have some code that does this. Right here, we choose, in this case, omega. And then I say W0 is equal to cosine omega, and W1 is equal to sine omega. Now we enter in our A matrix and select, find the eigenvalues and eigenvectors. And we now just create this linear combination where we have v colon comma 1, so the first eigenvector, times cosine omega divided by the square root of the first eigenvalue, plus the second eigenvector times sine omega divided by the square root of the second eigenvalue, and we plot them. And I'll show you a plot here in just a moment. Okay, so here's a version of our completed plot, and you notice it's a little bit different than if you're looking at the solutions that we had. It's oriented differently, and this is indeed the correct way. If you choose any value on that red circle and insert it into the equation x transpose ax, you get a value of 1, and you can verify this if you like. So this is the correct answer and the correct approach.